Alright, welcome back. If you're watching the early part of the first video, which is now changed to circular motion in magnetic field, that video is no longer there. Change the name, of course. This is continuation of that video, and we're now talking about the IB topic, which IB flux and Faraday's law, magnetic flux and Faraday's law. So this video is going to be about the magnetic flux and Faraday's law, and I'll be talking about what flux is and how does Faraday's law plays a role. I will not be talking about Lenz's law in this video, even though it's heavily related and explains about certain small but very significant feature in the Faraday's law formula, which I'll be working with. However, I will not spend too much time talking about that. That will be a separate topic here, which is going to focus on how flux and Faraday's law plays a role with each other. Now, recall that when a charge moves through a magnetic field, a moving charge moving through a magnetic field, the magnetic field will exert a force on that moving charge, causing that charge to move and accelerate, right? It's moving in a different direction. However, as we all know, motion is relative, right? Motion is relative, which means that what if a charge is stationary and it is in fact a magnetic field that is moving? Right? What if it's a magnetic field that's moving, a changing magnetic field? Instead of moving charge inside a stationary magnetic field, and the magnetic field exerts a force on it. What if it's a stationary charge, but the field is moving? Right? The field is changing. Okay, the field is changing. Then, in our understanding, then that field must be able to exert a force on that charge, right? But then the charge will start to accelerate. The charge will move. But let's say in our frame, the charge was not moving force. Suddenly, the charge start moving. That means you'll induce a current. And when it's a current, the only way for this current charge to move, that must mean there is going to be a potential difference, electromotive force, which is the voltage. So Faraday basically said, well, if a moving charge can create a magnetic field, the moving magnetic field must be able to induce a moving charge as well, which induce a potential difference, a electromotive force. And that is Faraday's law. But before you do that, I need to introduce a concept called the flux. Okay, in this here, it says electric flux. Okay, the exact same thing can be done for the magnetic flux, which is, I can just say the same thing. So essentially, what electric flux is, flux in general is the number of field lines passing through a surface. Doesn't matter if it's electric or magnetic. It can be gravitational flux. Okay, basically there's a flow, there's a vector field in presence. Could be wind flux, right? You have a vector field. Okay, you have a vector field in presence. Okay, and you have a specific area of object, and in the area, as you may think about what area you're talking about. Well, of course, circuit is loop, right? So it's a circuit loop. Anyhow, so if you have a specific area, and the object have a specific area in the field. Okay, and then basically the idea is the quote-unquote number of field lines passing through the surface. Okay, the total number of field lines passing through the surface. Of course, there are infinite many field lines, so you might think, what do you mean, number of field lines? No, that's just a way to think about it. Okay, but that's just a way to think about it. But really, what a flux is basically we account for the field strength, okay, and the area. Basically, the idea is the flux, by definition, the flux is just a field multiplied by the area of interest. So how much field is moving, how many vectors moving through the area? Well, given a fixed area, how much field is passing through the area? Right, so field times area. So electric field will be electric force times the area passing through. Right, this is the area here, and the field line. Cos theta, cos phi actually here. Don't worry about it. We'll talk more about that later. Okay, we'll talk more about that later. But basically, electric flux would be electric field electric field, times area, and the magnetic field, the formula for magnetic flux, of course, will just be the magnetic field times the area it's passing through. Alright, hopefully very straightforward concept. Alright, that's what a flux is. Alright. Alright, now, notice, okay, a field can only quote unquote pass through a surface if it's perpendicular to it. Okay, this image below illustrates that. So if a surface is parallel to the field, right, there's nothing going through the field, just go right above it and below it, there's no field going through this area. Only the perpendicular portion, right, has area going through it. And of course we expect larger area to have more field going through, right, so larger flux, okay, or if you have a larger field, you have more flux, you have more field going through it. Once again, it's an idea of how much the field goes through a certain area. So to do that, basically we're taking the idea. Okay, here is the idea. So if we consider that if this area, okay, if the area is perpendicular to the perpendicular area is perfectly aligned with the field, then we expect the amount to be 100 completely. Okay, completely. So effectively, the angle we take, phi, is the angle between the area, perpendicular component of the area, which is the normal, this we call the normal. Okay, and the direction of the field. So basically, the angle phi is the angle between the normal and the field. Okay, so phi, little angle phi, is, I want to actually, let me just double check the notation in the IB data book. So I am using a consistent notation here. Okay. Right. This is topic 11, of course. Just a quick check, notation. I am pretty sure I have it correct, just in case. Oh, theta, okay. Let's use this for theta as well. So, the angle between theta is the angle between the normal to a surface to the field, B, magnetic field. Alright, and then from there we can easily conclude, as you can see from the diagram, only the perpendicular component matters. Right, only perpendicular component matters. We can easily see that the flux is equal to magnetic field times area. Once again, we only care about magnitude, so I didn't draw the arrow, times cosine of the angle. Alright. Or you can think of the component where you can say area doesn't make any sense. For area to be perpendicular, sure, then you can say the perpendicular component of the field. Doesn't matter. Cosine theta is multiply. Okay, give you the same thing. Alright. Now, of course, normally when we have an experiment, we do not just have a single area. We usually have like a bunch, like a loop. And the field goes through that, right? Magnetic field goes through all of them. It goes all the way through. And we're moving this field through, maybe it's through the magnetic field, right? So causing it to change and inducing a charge in there, inducing an EMF in there. So you have multiple area loops in there. Well, if each area have the flux, you have n loops, right? N loops, n linked loops, right? that's very easy. So we just multiply the total amount by n. Okay, we just multiply it by number of loops, where an A is the number of loops. Very nice and easy. And that, of course, is called the magnetic flux linkage. So this is called the flux linkage. Basically, it's a fancy way of saying you have n loops linked together. I mean, I don't know, sometimes it won't sound fancy, but if you think about it, it's like, yeah, it's a bunch of flux linked together, so it's a flux linkage. Okay, nothing special there. Okay, nothing special there. Can't remember. Next slide is already. Oh no, that's a question. Okay, not yet. Now, okay, now here is what's interesting. Through experiment, okay, through experimentation, okay, Faraday found that when you move a area, a loop through a magnetic field, okay, through a magnetic field, what Faraday found is that you will induce, as he predicted, you will induce a electromotive force, and that is equal to the change in flux in a coil, which means he found that EMF is equal to the change in flux over time. And for those who are calculus savvy, the EMF, we're assuming the change is constant, but it's not necessarily constant, it's a derivative of flux over time. Alright, we're not going to worry about this version. Okay, we're going to worry about the simple version. And and of course that means there are of course two ways for this to happen. One is to remember phi is using phi is equal to BA. Well, one way, of course, is to change the magnetic field strength, but the area is fixed. So we can determine the strength of EMF based on how far the field changes. This is something like if you move a magnet, you have a loop, wire, maybe it's connected to something, right? It's a wire, it's a loop, and the magnet moves in and out, right? It gets closer, it gets further. Okay, it either gets closer or gets further, so depending on how fast it gets close and how fast it gets out, that will determine how fast the field changes, right? How fast the field changes, that will induce a current. Or you can change it by keeping the magnetic field as constant and change the area, which is similar to something like this. Let's say this is a magnetic field, and then you have a loop here. However, on the loop, and this end is actually free to move, right? This end's free to move. So area inside, so you can move this line, you move this bar left or right, okay, left or right, and then that's not the only way, of course, but just to give you an example, moving the line left to right, the field won't change, but moving the line left or right, you notice the area will increase or decrease. Moving left, it will decrease. Moving right, it will increase. Right? Moving left, it will increase. Moving right, it will increase, I mean. So by changing the area, you'll also induce a current inside this loop here. Induce a current, and if there's a current, there's going to be electromotive force, okay, based on the resistance and so on. Okay? So there are two ways to induce an EMF. There's actually a third way, motors, but or something we'll talk about a little bit later. Okay. Now, you may remember that when we actually practically, and when Faraday did the experiment, he and we don't just move one wire, one loop through. It's a bunch of loops. So, what do we do? Well, very easy. So if there is a bunch of loops, let's just do the case 1 example. You have a magnet, you're moving through a bunch of loops instead of one, with n loops, then the EMF induced just piles up because each loop experiences the change in magnetic field. So it's n times the change in flux over time. However, interestingly enough, the Faraday's law version we know now actually has a negative in front. Why is there a negative? Well, why is what we'll need to talk about a little bit later. It's called Lenz's law. But right now, we just accept this negative. Negative just means, okay, negative here just means that the induced current will be opposite the change in flux. Okay, it has direction. Okay, it's not arbitrary. It does depend how your magnet moves. So this actually indicates direction. Okay. Yes, EMF is a scalar. It's a voltage, right? Doesn't have a direction. This actually indicates direction of the current. Okay, I'll talk more about that when we talk about Lenz's law. Which means direction actually matters. So how the field change actually matters. It's not just the field change. Okay, well, how the field, like if it's north going in, right, then you would current one way, south going in, you'll be a different direction, right? Because how the field changes direction, because north is away, south is towards. So the direction actually matters. Okay, that's all it means for now. Okay, for now. So that is the formula for Faraday's law. Okay, that's the formula for Faraday's law. Now, let's take a look at some examples. So for instance, which experiment, the maximum voltage is 18 volts. What happened if the reverse magnetic south pole goes in first, and what would the effect of doubling oscillation be? Now I'm going to do this one. We have to actually watch an animation, so let me load that animation up. You'll hear the sound, but I just need to switch my display over. Let's try it again. There we go. So notice when it's moving in, it deflects right, and when it's moving out, it deflects left. All right. So that is the what's special about it. So when it's moving in, it's deflecting towards the right. When it's moving out, it's deflecting left. Right? Deflecting left. Very simple. So go back to our notes. Then, as we know, the negative sign in front indicates direction matters. So, if north and south reversed, direction of the flux changed because north it was going away, south is going towards, so direction of the field changed. So, direction of B changed, reversed. Therefore, the flux changed direction. Therefore, the EMF will change direction. Or you can say, or more specifically, I can say the current will change direction, right? According to Faraday's law, the negative sign in front indicates that direction matters. Okay, so a current will change direction. Okay, which means if south pole's first, if moving in would result earlier, moving in would deflect right. Now the needle will move left. Right? And then out will cause the needle to move right. So it's reversed. The direction of the current is reversed. Will move right. So it's opposite of what you see in the animation earlier. Right? So that's what the negative sign means for now. Why? We'll talk about that when we talk about Lenz's law. Now, B. what happens if we double the oscillation speed? Double oscillation speed. Well, as we know, right, V is equal to D over T. I'm assuming it didn't increase the distance it moves, I'm assuming, right? Which means speed is inversely proportional to time. Which means if we double the speed, that means we halved the time. Right, we halved the time. So now remember that the induced EMF is equal to N times changing flux over changing time. Right, the negative sign doesn't really matter here because we're not knowing about direction. The direction doesn't really affect how time changed. Right, the oscillation and the direction are still the same, so the direction doesn't really matter. I'll leave it here. Specifically, we know that EMF is also inversely proportional to time. So, since time got halved, there's only one conclusion: the EMF must double. So the induced EMF doubles. Now, the third question says, what is the expected EMF for one loop? Well, let's count how many loops there are. Alright, we have one loop here, 2, 3, 4, 5, 6, 7. There's 7 loops here. So we know EMF is equal to 7 times delta phi over delta t. That is about 1.8 volts. Right? We care about one loop. This is for 7. We care about 1. So which is just good old delta t. That of course will be exactly divide both sides by 7. 1.8 volts divided by 7. Counting. Wait, let me quickly plug that into the calculator. 1.8 volts divided by 7. I get 0.26 volts. Right, 7 is counting, so don't worry about sig dig. Oh wait, 1.8, 18 volts. Oops. 18 volts. So it's not 1.8, 18 volts. So this one 0.26 will be 2.6 volts instead. And then D, of course, is 150 loops. Then epsilon 150, which is equal to 150 times delta phi over delta t, which is 150 times 2.6 volts, which is about 390 volts. Check. Times 150. I got a value, 2 sig digs, 118, not 8. 390 volts. 2 sig dig, right? So there it is. Okay. Very straightforward application of Faraday's law. So this will be an example of Faraday's law. All right, let's do one more, a little bit different. What's the magnetic flux of a coil has 500 turns, and it's graphed in as shown here. Okay, so how do we calculate the induced EMF? Okay, induced EMF. Remember, it's 500 turns. All right. So the flux, the change in flux over time, of course. Okay, a change in flux over time, of course, is equal to the slope, because the y is exactly the flux. So changing this is because this is y, this is x. So this is exactly changing y over changing x. Or alternatively, we can say, right, EMF is equal to delta phi over delta t. I guess you could say n in it, right? N. And then the y is changing flux times changing t. So so you can rearrange. So delta phi is equal to delta t times EMF divided by n. Right? So the slope is equal to EMF divided by n. Either way, so EMF is equal to n times the slope. Well, I should probably do the y equal to mx plus b. So if I rearrange this, I will get this over n. So that's my y, that's my slope, and that's my y-intercept, which is 0. So therefore, slope is that, and the y-intercept should be 0, which it is. Slope is equal to that, so y is equal to slope. Either way, we have to calculate the slope. So slope, let's pick this point, I guess, and let's pick the point at near 0. Let's pick close enough to 0. Sure, let's use that. We don't have to pick 0, okay, but 0.0, I guess, still 2 sig-digs. All right, so this one will be, this looks like 4 or something, so 4.0. So the slope is equal to change in y, which is 2.00 times 10 to the negative 3 Webers, that's the unit. It's a unit for Tesla meter squared is Weber, divided by minus 0. Minus 0.00 times 10, I'm just going to say it's minus 0. Divided by the x value, which is 4. 4 times 10 to negative 3 seconds. 4.0, we cannot be certain, so we have to certainty. 4 and 1, 2, 3, 4, 5. So it's 4.2, somewhere between 4.0 to 4.2. So 4.0 is a good estimate, times 10 to the negative 3 seconds. When we do that, we get a value of, it should be 2 sig-digs, so 0.50, okay, 0.50 volts. And then we just multiply it by 100, so it's 500, times 0.50 volts. And we get a value of, well, 250. Right? So the correct answer here is C. Another application of Faraday's law, very straightforward. I didn't originally plan this, but I think since we're already here, might as well try one more. One last application of Faraday's law is actually we can get this explicit formula for the moving loop example. Okay, what's current induced in here? All right, area with a constant field. B. All right, so we'll actually calculate exactly what's induced EMF in here as area changes. Let's say this loop is infinitely long, as this is moving this way at speed v. Right? Let's say the distance between the length of the conductor, basically the length of the conductor is fixed at L. Okay, and this is distant, and this distance here, let's call that x. Right? That's x. Then we know area is L times x, and of course x is changing. So the induced EMF is equal to, there's only one loop here for sake of simplicity, there's only one loop here, so it's just good old change in phi over change in time. And of course the field is constant, so what's actually changing is the area, as I mentioned, over change in time. However, not the entire area is changing. The length didn't change, right? The length didn't change. What's actually changing is the x component. That part is moving, changing x over time. So how fast this distance is changing? Now, what do we call a change in distance over time? Well, it's just the speed is moving. Right? It just changed, speed is moving. So we get a formula that in this scenario for moving conductor through magnetic field, okay, outside the rail, we get that's BVL, and that's a formula. So EMF is equal to BVL for a moving conductor of length L moving in field B, okay, at speed v. At speed v. So that would be the formula for a moving conductor as well. And of course, if you have a bunch of moving loops, a bunch of conductors moving at the same time, then it's just N B V out. And it's number of loops once again. Number of conductors moving at the same time. So no change there. Nothing surprising over there. All right, wrapping it up, the last thing I want to introduce is actually pretty straightforward. Now, if we know the flux, right, if we know the flux, it's known. What do you want to know? The flux density, which is what's the average flux per area, which means the flux density is equal to the average flux per area. You may notice that is just the magnetic field. Same thing. So flux density and field strength, magnetic field strength, are one and the same. Just like gravitational acceleration and gravitational field are the same thing. Flux density and magnetic field strength are the same thing. It's just where do we use it at? Are we using magnetic field strength to calculate the strength of magnetic field and to calculate the magnetic force? Then we treat it as magnetic field strength. Or instead, we want to look at how flux is distributed, how dense flux lines are, then we treat it as flux density. They're exactly the same thing, it's just how we use that value. All right, and that is Faraday's law. Thank you for watching. Have a great day.